For any help-related queries, call us at +1 678 648 4277. You can mail us at support@mathhomeworksolver.com or reach us at https://www.mathhomeworksolver.com. Problem 1. Let L and M be finite-dimensional linear spaces and let F, L, M be a linear map. Prove that the subspaces Ker F and IMF are finite-dimensional and dim Ker F plus dim IMF equals dim L. Hint: use the extension of a basis theorem. Problem 2. Consider the space L, V, of linear maps from a finite-dimensional real linear space V to itself. Which of the following subsets of L, V are linear spaces? A. FL, V, dim IMF equals 0, B. FL, V, dim kerf equals 0, C. FL, V, dim IMF dim V. Reformulate the obtained results in terms of matrices. mathhomeworksolver.com. Problem 3. A. Show that there are no finite square real or complex matrices X and Y such that XY minus YX equals I, where I is the identity matrix. D. B. Check that multiplication by X and differentiation are linear dx maps on the real or complex space P of all polynomials in 1D variable X. Compute the action of dx(x minus x) in P. Here dx denotes the composition of two maps. C. Introduce the concept of a matrix with infinitely many rows and columns. Define the multiplication for infinite matrices in which each column and each row has a finite number of non-zero elements. Using B, find a solution for xy minus yx equals I in terms of infinite matrices. mathhomeworksolver.com. Solution 1. Let L and M be finite-dimensional linear spaces and let F, L, M be a linear map. We want to show that IMF and Ker F are finite-dimensional and that dim IMF plus dim kerf equals dim L. We assume that dim L equals N. Let Bj be a basis for kernel of F. By the basis extension theorem we know that there are linearly independent vectors, Ck, such that the ordered set, Ai equals Bj, Ck, forms a basis for L. Since the total number of basis elements for L is finite, it must be that Ker Fl is also finite dimensional. Thus, dim Ker F equals L less than or equal to N. Next we show that F, Ai, N span IMF. We choose V IMF. Since I equals L plus 1 N Ai spans L, there exists scalars D such that V equals F, such that V equals F, di. Noting that I equals 1 F, Ai equals 0, 1 less than or equal to equals 1 F, Ai equals 0, 1 less than or equal to I less than or equal to L, we have V equals less than or equal to L, we have V equals IN equals L plus 1 CIF, AI. Thus, F, AI, IN equals L plus 1 spans IMF. F. To verify the linear independence of F, AI, N we consider the linear Ni equals L plus 1 and combination I equals L plus 1 CIF, AI equals 0. Then by linearity Fi equals L plus 1 Ci equals 0. Since Ai are linearly independent it must be that all Ci equals 0. Hence all N, F, Ai, I equals L plus 1 are linearly independent and we can consider them a basis for IMF. This also confirms that IMF is finite dimensional. Hence, dim IMF plus dim kerf equals dim L. mathhomeworksolver.com. Solution 2. A, FL, V, dim IMF equals 0. This is a subspace. The defining condition of this subset is equivalent to F equals 0. Thus, for all V, F, V equals 0. By linearity, this is also true for any combination of such linear maps. Considering the matrix representation of this subspace of linear maps, we conclude that it is isomorphic to the subspace of zero matrices. B, FL, V, V, dim curve equals 0. This is not a subspace, unless dim V equals 0. We prove this by contradiction. Suppose V, V. Then necessarily for F in the subset, F, V, equals 0. Further, by linearity it must be that Kf, V, equals 0, Kf. We pick K equals 0 and then for any vector V, V, the action of Kf on V gives 0, independent of V. Thus dim cur Kf equals 0. However, if dim V equals 0 then also dim cur F equals 0. In this case V, 0, and necessarily F equals 0. Formulated in terms of matrices, we can consider this subset of linear transforms isomorphic with the set of matrices with rank equal to the dimension of V. This is not a subspace since multiplication of any such matrix by 0 will result in a matrix that has rank less than the dimension of V unless the dimension of V is 0. MathHomeworkSolver.com C, FL, V, V, dim IMF dim V. This is not a subspace, unless dim V equals 1. We prove this by contradiction. Let dim V greater than or equal to 2 and let I equals 1 be a basis for V. Further, let phi aj for I equals j and phi aj 0 for I equals j. Then for thus, dim imphi equals 1 dim V equals ni equals 1 ci phi V equals ci V equals. However, nn phi V equals V and dim im phi equals n equals dim V. For dim V equals 1 I equals 1 I equals 1 it must be that F equals 0, dim IMF equals 0 and proof follows as in part A. We cannot have dim V equals 0, since then dim IMF equals dim V. We can consider this subset of linear transforms isomorphic to the set of matrices with rank less than the dimension of V. For dim V greater than 1 we consider a subset of such linearly independent matrices of rank 1 and note that the sum of these matrices may result in a matrix of rank dim V. In case dim V equals 1 our subset is a subspace of zero matrices as described in part A. Solution 3. We want to prove that there are no finite square matrices such that xy minus yx equals I. By contradiction, suppose we could find such x and y. Let x, y, I f m times m. Then trace xy minus yx equals trace I equals m. However, MathHomeworkSolver.com. Thus, it is impossible to find finite square matrices that say us phi xy minus yx equals I. Both of these maps are linear. MathHomeworkSolver.com. We calculate the compositions of these two maps. MathHomeworkSolver.com. C. We introduce the concept of matrices with infinitely many rows and columns. To define multiplication of two such matrices, we restrict our attention to matrices with finitely many non-zero elements on any given row or column. Then, for any given row by age, infinity there j equals 1 exists a number ni such that age equals 0, for j ni. Similarly for any given column, age, infinity I equals 1 there exists a number mj such that age equals 0, for I mj. Multiplication of two infinite matrices A and B is then defined as. In order to construct the matrix representations of linear transforms X, and we consider their actions on the standard basis ELE dx ment xk. For k greater than or equal to 0, xxk equals xk plus 1. Similarly for k greater than 0, d xk dx equals dkxk minus 1, k equals 0, dx